Welcome to the Quantum Leap, a look inside the 2025 Nobel Prize in Physics, awarded for unlocking macroscopic quantum tunneling. We'll explore the work of laureate John Martinis, who noted, "You can become God, but nature doesn't make that easy." The Nobel Prize recognizes a discovery that's a, quote, 40-year vintage. John Martinis proved macroscopic quantum tunneling in 1985. This discovery, which involved the creation of an electric circuit that follows quantum laws, aged like fine wine before transitioning to an industrial sector. This work centers on the paradox of the artificial atom. Typically, quantum mechanics governs microscopic atoms. Martinis proved that a visible electrical circuit, though macroscopic, could be engineered to behave like an atom, obeying quantum laws. The core phenomenon is macroscopic tunneling. Classically, a particle bounces back from an energy barrier. Quantum mechanically, it can tunnel through. The trick involves the system borrowing energy for a tiny fraction of time, permitted by the uncertainty principle. The engine for this process is the Josephson junction. Created by oxidizing aluminum wire, this component forms a barrier thin enough for tunneling. Cooper pairs, which are electron pairs in a superconductor, tunnel across the junction, creating a quantum current without resistance. This creates the artificial atom. Martinis also challenged the myth of instantaneous tunneling. He calls the time it takes to tunnel tunneling traversal time. His experiments showed that the tunneling rate changed based on distance to a resistor, implying the system only, quote, sees the resistor after a speed of light delay. This is crucial for engineering complex quantum circuits. These concepts bring us to the qubit. A quantum bit exists in superposition, simultaneously holding both 0 and 1. This phantom zone of ghostly probability collapses into a single hard data point only when measured. The power of quantum computing is exponential. With just 53 qubits, you can process 10 to the power of 16 states in parallel, the scale of Google's Sycamore. At hundreds of qubits, the computational space exceeds the physical matter of the observable universe. The challenge is identifying the one correct answer among trillions of possibilities. Engineering the impossible requires overcoming heat and noise. The solution is using superconductors, which have zero resistance and operating at extreme cold, near absolute zero or millikelvins. Martinis compares the required environment to the permanently shadowed craters on the moon, the only places quiet enough for these calculations. Achieving quantum supremacy means performing a task practically impossible for a classical supercomputer. A calculation that would take a classical supercomputer 10 to the power of 25 years is completed by a quantum chip, like the recent Willow, in minutes. A key application is the future of encryption. While Shor's algorithm suggests quantum computers can crack current RSA encryption, the reality is that current crypto is simply nearing end of life. The fix is quantum-safe crypto, standardized by NIST. As Martini states, you can sleep well at night. Quantum computing is essential for simulating nature. Key applications include modeling molecular bonds for drug discovery, solving differential equations for atmospheric physics, and mapping the trillions of synaptic functions in the human brain. The logic is, it's quantum all the way down. The future lies in quantum plus AI. Quantum computers will serve as co-processors for massive AI supercomputers. An AI identifies a hard physics problem and offloads it to the quantum processing unit, or QPU. These powerful technologies require governance similar to the Atomic Energy Commission of the past. Quantum computing is currently in its 1950s era, room-sized, fragile, and experimental. You won't have a quantum phone. Future access will be via the cloud. The goal is accelerating development to make the technology fully useful within our lifetime. The quantum leap shows how basic science can feed into industry. The 1985 discovery of macroscopic quantum tunneling, which seemed abstract then, has birthed a new computational era in 2025. Support basic science. You never know what seemingly useless discovery will build the future.